Hi everyone. Today we are presenting our paper Latency Measurement for Autonomous Driving Software using Data Flow Extraction. This paper was presented at IV 2023 and is a joint research work of the Technical University of Munich. Today we have many robotic systems that heavily rely on ROS2 middleware and software architectures. Unfortunately, due to the increasing number of functionalities, it is very hard to keep track over the latency and data flows inside the software. Especially when it comes to safety critical systems, we heavily rely on real-time constraints. And since we have many robotic applications today, the software is getting more complex than ever. Especially when we look at those safety critical systems, for example, autonomous driving software. On the right side, you see the AutoWare software stack consisting of perception, planning, and control modules that are enhanced with sensing, map data, vehicle interface, and localization modules. In order to make an autonomous car drive on a street reliably, it needs many modules that then consist of submodules, and as you can see here, is getting more and more complex. For example, if you look here on the right side, you see the node diagram of AutoWare Core in Universe, which consists of many high modules and submodules. So the question arises, how do we find flow of data in large systems? Because we have this large number of modules, the large number of developers, and ultimately a constant change. This is the question we are tackling in this paper. When searching for the research gaps, we find many other research today that is tackling the field of latency analysis, end-to-end analysis, handling of entry nodes, and handling DDS software, especially for ROS2. Most approaches today rely on ROS2 tracing, and only a few approaches tested on large robotic applications, for example, autonomous driving software. Ultimately, none of the work presented today is having a highly automated process. Right now, the automatic data flow extraction is not existing. Right now, a considerable manual effort needs to be done to have the data flow extracted. Ultimately, little guidance on how to do the manual data flow extraction is given, and no fine-grained analysis of idle, DDS, and computation times is presented. We therefore find our research gap and ask us the question, how can a ROS2 robotic software architecture be automatically analyzed to measure the end-to-end latency? We therefore create some sub-questions. How can the latency of an overall ROS2 software be measured? How do we find the flow of data, especially in large-scale robotic systems? How can the individual components of the end-to-end latency be analyzed? And therefore, we create not our question, but our goal. We want to build a framework and tool to analyze the data flow in ROS2 applications to get a deeper insights into latency times and module dependencies. We therefore create our own methodology and therefore our ROS2 latency framework. First of all, we start with the ROS2 application. In our case, we are choosing an autonomous driving software stack. For you, you can choose whatever robotic ROS2 software architecture you have. We then apply ROS2 tracing and add a static code analysis. By combining the static code analysis and a ROS2 tracing, we can create autonomously or automatically our data flow graph. And with that data flow graph, we then ultimately have the chance to do the latency measurement, to get the info about end-to-end, idle, communication, and computation time. But how do we do that in detail? First of all, we need to collect. We need to provide a robot ROS2 software. As presented here, we have an autonomous driving software. Then we need to collect the tracing data from simulations. You can do that on a real robot, but in our case, we are running simulations only, which is totally enough. And then we need to collect the node internal data flows from the source code. Then for us, it's time to analyze. First, we need to assemble the data flow graph, then extract the messages flows on the path, and then calculate the path statistics. This is basically how this ROS2 latency framework works. Now we step a little bit more into detail. First of all, let's have a look at the ROS2 tracing. We are using the well-known ROS2 tracing because the ROS2 tracing provides us, number one, the ROS nodes, the node callbacks, the topic, subscription and publishers, and the timers. But this ROS2 tracing right now is not enough. We are missing the callbacks to publish a topic and the data flows between the callbacks. And that's exactly what we then do with our static analysis. We apply now a static analysis of the ROS2 node, which provides us the data dependencies in between the callbacks. How do we do that? What you see here on the right side is our static analysis. Our goal is to find all the data dependencies between the callbacks. The idea, we find all variables accessed by multiple callbacks. We can then record the dependency for callbacks that access the same variable. And in the execution, we are using the Clang matchers. What you can see here is now our application of the Clang matchers. Our goal is to find matching patterns inside the code. For example, what you can see here in a C++, our mynode, the RCLCPP node mynode, and we try to find that matching patterns with our Clang matchers. And therefore, we can now apply a static analysis of the code. When we're done with that, we now ultimately combine the two things we just explained. We combine the ROS2 tracing and we combine the static analysis with the Clang matchers. And therefore, we find now the callback publisher relation through timing relation. In summary of the AutoWare software analyzing, we have 19 matches implemented. We have the complex C++, which cannot be handled autonomously or directly, and then have the direction of the data flow not always apparent. For us, we record all data flows that could exist in each node, and the superfluous paths must be filtered out later. As the result in our metric definition, you can see here now a static and data flow analysis of our AutoWare software stack. What you can see here is an overview of 4 different nodes: the LiDAR node, localization node, the planning node, and the controller node. What you can see here with our analysis, we have now the possibility to first of all define the end-to-end latency from the beginning, from the sensor to the end to the controller. We can then define now the idle times displayed here in orange. We can define the computation times, how much time it takes to compute, for example, the processing of the LiDAR, the callback runtime, and ultimately the DDS time. And here you can see that with our analysis and the method presented here, we have the possibility now to get the information of all the times. As a summary and one of the results, you can see that for AutoWare, we have displayed here 12 nodes, 15 callbacks, 12 topics, and 3 internal data flows. For us, we have now the possibility to have the complete sensing, localization, planning, and control integrated in our analysis, and therefore can display exactly what happens inside the modules, the relationship, the dependencies, and ultimately the times. For example, another result is what we displayed here is a baseline of a sensitivity analysis. We put the AutoWare software stack on our vehicle hardware and run some simulation, and we could ultimately display what kind of end-to-end idle and communication computation times we have. With our analysis and the latency measurement framework presented in this paper, we were able to display that number one, the idle time occupies the largest portions of the latency. Number two, ROS2 and AutoWare right now are not yet real-time capable. And number three, the latency must be reduced by applying optimizations. We therefore could provide for AutoWare a detailed analysis of their whole software stack. Ultimately, we know that this work is definitely not the end. What we could present here is that our latency measurement is highly automatic. There's no manual intervention anymore needed. Number two, we have a novel application for static analysis for ROS2 latency analysis that can be applied to any robotic ROS2 software. And number three, we can provide an in-depth analysis. Our future direction is that we want to provide extensions for the static analysis approach, optimize the ROS2 layer, and apply this framework to many more ROS2 applications. Our key takeaway for you is that we developed a framework for the analysis of ROS2 robotic architectures regarding data flow in order to provide latency measurements. Therefore, thank you very much for listening. If you're interested to read the paper or get our GitHub code, please have a look at the websites. Or if you want to get to know our lab a little bit more, here is the link to our lab website. Thank you very much for your attention.